So I rewrote this problem and did it in a separate video because this problem is really involved and has a lot of different steps. This is an indication of what makes integrals really challenging. And our answer to this is going to be pretty complicated. So the first thing to do is it kind of looks like something we can use U-Substitution on. So I can see if I can use U-Substitution on it. Okay, so u equals x squared minus 10x plus 29, because the bottom looks kind of like the top. And so du over dx equals 2x minus 10. I don't have a 2x minus 10. I have a 4x minus 11, and I can't multiply 2x minus 10 by anything to get 4x minus 11. I can line up the 4x. So du equals 4x minus 20 dx, but I multiplied this side by 2, so I also got to multiply that side by 2. So I get that 2 du equals 4x minus 20, but I don't have a 4x minus 20. I have a 4x minus 11. So we actually do two different integrals here. We do one for the first integral being my U-substitution integral, where I have 4x minus 20 over x squared minus 10x plus 29 dx. So that's one of my integrals where I use the U-substitution. But if I do 4x minus 20, to actually get what my original problem was, I'm like neglecting 9. Like that's the difference. If I rewrote the top with the 4x minus 20, 4x minus 11 would be equal to 4x minus 20 plus 9, because negative 20 plus 9 is negative 11. So if I do this, I need to have a term with 9 left over. So I have to have another integral where it's 9 over x squared minus 10x plus 29 dx. This guy, I'm ready to integrate. I already have my U-substitution set up, so I'm going to do this guy real quick. And I get, I said the top was 2u, 4x minus 20 dx is 2u, 2 du. And on the bottom I just have u. So I'm integrating this, and I get 2 natural log of u. I'll plug in what u is, x squared minus 10x plus 29. And that's it for that one. I could do plus c, but I'll put plus c way at the end when we're done with the other one. Okay, now for the fun one. This is going to be one of our inverse trig guys. And when you don't see a square root, and you see a constant over x squared situation like this, your mind should jump to that looks like the tangent. So I'm going to use inverse tangent here. Specifically, I'm going to use the equation that, and I'm going to write an equation here. I'm going to use to solve this. This is out of the book. Du over a squared plus u squared is equal to 1 over a arctan of u over a plus c. So we need to make our thing look like this so we can use this equation. This necessitates completing the square. Like we have to use completing the square to get something squared plus something squared. So I'm going to complete the square on this bottom. So I'm going to divide by 2, and I get negative 5 as my b term, which means x minus 5 squared is the thing that's going to yield me the x squared and the minus 10x. And we can do that by foiling. X times x is x squared. X times negative 5 is negative 5x. We have 2 of those, so negative 10x plus 25. So x minus 5 squared is what I'm going to throw on the bottom. Now, to actually get x squared minus 10x plus 29, I need 4 more. So my new bottom is going to be 9 over x minus 5 squared, and that takes up 25 of my constant term, and I need 4 more on the bottom to actually match my original guy there. So I've used completing the square to rewrite this guy so it looks like this. So now my a is actually the constant term, so a is 2. My u is something with a derivative of 1, so it's actually just, this is a really nice one. And like I could say u equals x minus 5 and du equals dx, but I mean really I've just rewritten it with u's. I don't really need that here. And the 9, just I could pull it out in front. I could do a 1 here and a 9 there. That would be fine. And so if I integrate this, I get 9 times 1 over a is the first thing I get. So 1 over a is 1 over 2 times the arctan of my u is x minus 5 over 2 plus c. So the actual answer was, this was the answer for part 1 and this was the answer for part 2. It's 2 natural log of the absolute value of x squared minus 10x plus 29 plus 9 halves arctan of x minus 5 over 2 plus c. And really, this integral is the beginning of the compelling argument for why integrals can be a lot harder. I was talking with other teachers. Let's just end.